Welcome everyone to the August 2019 monthly webinar series from Phase 1 Industrial. At this webinar, we've invited one of our integrating partners, Teledyne Optech. Now, Teledyne Optech has done an amazing job integrating the Phase 1 sensor into their LiDAR system. But before I turn it over to Mark Topping, the Regional Sales Manager from Teledyne Optech, I want to briefly review the Phase 1 corporate and products that are offered in systems. Now, we are a leading provider of the medium format digital imaging systems. When you hear about medium format, Phase 1 is typically synonymous with this. We've come a long way since we've started the industrial group. We're no longer just considered a camera provider. We provide systems, solutions that's comprised of both hardware and software. This here is an image of our Broomfield office in Colorado, USA. Now, although being a trusted brand, a market leader, and having worldwide distribution, we have R&D centers around the world, from the brain or the body of the camera, lenses, and programming teams for the software. So we certainly have a worldwide coverage and 24/7 support. Now let's talk a little bit about the technology that Phase 1, the edge that we have in this market space. As you can see from the product offerings, anywhere from the 50 megapixel for UAVs to the 190 megapixel for wide area coverage, we have the best talent around the world respects to camera technology, systems technology, and delivering software. And because of that, we can offer such a diverse product and solutions offering. Here's our camera line that we offer at the kit level for cameras. Now, interestingly enough, we talk about Teledyne Optech being part of this webinar. They were customers or partners integrating cameras from this point even before these particular cameras are on the market. So we have from left to right is the IXU series cameras, the IXU 1000, the IXU 1900, that's the 190 megapixel. So these IXU RS cameras are really for the manned aircraft flying at high altitudes, and in Cessnas as well. Moving over to the right is the IXM series. Now the IXM series is very specific to the drone or UAV world. We do use some of those cameras though in oblique systems that Phase 1 offers. And then you have the IXM-RS. So that is currently really the bread and butter or the popular camera that we offer today at the 150 megapixel resolution. You'll notice at the bottom of this slide, there's RGB offerings and there's achromatic offerings. What this means is if we combine two of those sensors together, we have a 4-band system. And in 2019, the 4-band system has been an extremely popular kit and a system that's been offered to different markets. The 150 megapixel being the most common 4-band system that's been popular this year. Now, although we're talking about Teledyne integrating with LiDAR and dual payload systems are very common in the mapping market, there are times when the mapping market says, hey, I just need aerial imagery. And it's because of that, Phase 1 has complete aerial imaging systems. And you'll see the range from either 100 megapixel single camera up to a multi-camera oblique system and choice of different INS IMUs, as well as camera and lens focal lengths. Again, when we talk about from the popularity standpoint of what's most common today, our 150 megapixel 4-band system is the most common. And then the next question is, well, what type of markets are these particular systems or cameras most popular in. So up on this slide is a wide variety of applications. And the nice thing about phase one is it's not a one size fits all. We have custom systems that are built for and optimized for specific applications. We talk about 4-band systems. We look more in the agricultural, forestry, or environmental mapping. Some of the corridor mapping for transportation and or utility or pipeline are also common for 4-band systems. So hopefully that's given you some well-rounded information about phase one. And as now is the time that we turn this over to our invited partner. In this case, it's Teledyne Optech. Now, there is a chat message window that you can type in your questions, and at the end of this presentation, we will review some of those questions and answer them. So at this point, I'm going to turn this over to Mark Topping, the Area Sales Manager for Teledyne Optech.
Thank you very much, Dana. Now, I know many of you are expecting Michael Sitar today, but it's your lucky day because you get me. So unfounded bragging aside, my name is Mark Topping, and I'm very excited to be sharing the capabilities of our integrated LiDAR and camera products with you all in this session. As Dana mentioned, I'm a sales manager with Teledyne Optech and have spent the better part of the last 6 years assisting our customers install, configure, and fly airborne LiDAR products with phase one's medium format products throughout the world. Now, I do have a distinct interest in LiDAR and imagery integration. These two types of sensors offer unique advantages, with LiDAR producing very accurate three-dimensional measurements, which can penetrate vegetation, and the imagery providing extremely high resolutions and color metadata. But I have to admit, winning is a good term to describe this webinar, because you can combine these two instruments in a single platform, reap the benefits of both, and access opportunities for your business that only this combination can provide. Applications of note go beyond 3D urban modeling. We can combine these two sensors in areas where the LiDAR can identify and measure features, and the camera can provide a visual inspection for engineering, transportation, utility projects, to name a few. Then there's applications where the camera adds to the LiDAR points to include an NDVI index, improve classification, classification confidence, and feature extraction. Now, before I begin, I'd like to thank Phase One for putting this webinar together. And as someone who has spent countless hours using their products, my unbiased, honest opinion is that the ease of use and imagery quality from these Phase One products is fairly unmatched for a medium format camera. So kudos to Phase One. Okay, let's begin. In this session, we'll be covering the specifics of how Optech has incorporated the Phase One aerial cameras into its complete LiDAR workflow. This will include 4 subsections on mounting configurations, flight planning, airborne operations, and data collection and processing. My goal for you today is to have an understanding of the camera features available to Optech LiDAR users, as well as Phase One camera users. So this is the Galaxy Prime you're seeing on your screen. It's Optech's current LiDAR unit for both wide area and corridor LiDAR applications. It's also the most compact and efficient sensor on the market today. So here's why Galaxy users have been successful in the past. The compact size. It's the smallest, the lightest, the lowest power draw of LiDAR of major LiDAR units on the market today for wide area. It also has a dynamic field of view, which can compensate for terrain change, the only scanner of its kind. So that really maximizes the efficiency of this sensor. It's also very versatile, very customizable, very programmable, so you can use it for your low altitude corridor missions as well as your higher altitude wide area type work. 100% effective points on the ground means that the laser pulse rate is the same number of points that actually leave from the sensor. You have a complete workflow, complete operating envelope, and all those points wind up as measurement points. The scanner has built-in roll compensation, and some of the most impressive precision and repeatability data results, particularly in smooth surface repeatability. Now, the form factor of the Galaxy is also protecting your investment in that Optech does incremental improvements on this sensor. You don't have to buy a whole new sensor with a different form factor and do a different installation every time you wish to stay competitive with updating technology. And we mentioned collection efficiency. We've seen in real planning scenarios 35 to 50% cost savings on customer endorsed projects, particularly in mountainous terrain where SWAT Track can adjust for the terrain relief. Now I'm going to show you the phase 1 medium format metric cameras that we have tightly integrated with the Optech products and through every step of the Optech workflow. These can be purchased together or as add-on to an existing LiDAR. The 100 megapixel RGB camera, which Dana mentioned previously, the IXM and the IXUs, as well as the 4-band dual cam setup, where we use an RGB and an NIR camera on the same mount as the LiDAR. The 150 megapixel is a camera we've recently added to our product suite with the Galaxy and other Optech products. And we also offer the dual RGB to achieve extremely high resolutions, up to 190 megapixel. And lastly, these are all controlled using the Optech LiDAR and the phase 1 products using the phase 1 IX controller. The Galaxy and IXM camera combination is the most common hardware configuration. You'll see this on the bottom left of your screen. These are available on fixed vibration isolated frame for your fixed wing, rotary wing aircrafts over a pressurized or a non-pressurized survey port. So just in the bottom left, you'll see the Galaxy on an isolated sled with an IMU and a phase 1 camera. In addition, there's the minimum dimensions in general for the port of your aircraft would be about 12 inches. And that's based on the distance between the camera and the LiDAR. So you can use them both through the same survey port in this fixed mount scenario. It's also available on a gyro-stabilized mount, as you see on the right, and in an external pod configuration with a carbon fiber sled. You'll see these on the bottom right. So the carbon fiber sled gets mounted into the helipod, which has specific installation kits for common configurations like the Bell 206 and 407. So I did just mention pressurized configurations earlier. If this piqued your interest, we also have a new compensating wedge for pressurized installations. Now, the best way a LiDAR pulse penetrates optical glass is at a 7-degree angle. For this reason, we manufacture a mount at this pitch with a nadir-looking camera counter wedge to accommodate these users. The red arrow in this picture actually shows how the LiDAR is pitched for glass penetration, but the camera is not. So you can use both of these. This can also be useful for semi-oblique LiDAR applications. You have a 7-degree pitch angle on that. Now, the Galaxy is not the only product we include a phase 1 camera set. All Optech products are able to send trigger signals to IX Capture, which is the phase 1 airborne operation software. If you're not familiar with IX Capture, I know phase 1 offers helpful training sessions for aerial use. Now, on the left side of your screen, you'll see the ALTM Titan, which is Optech's multispectral LiDAR system, the only one of its kind. With 3 independent wavelengths featuring green and NIR channels, you can improve topographic mapping, shallow water bathymetry, vegetative mapping, and environmental modeling applications. The Eclipse on the right is our low altitude corridor mapper, which is fully autonomous without an operator. This too has a plug and play option with the IXU and IXM products. On the topic of mounting, lastly, Optech can configure up to 5 oblique cameras looking downward and in all 4 directions on the carbon fiber mount with the Galaxy. You'll see an example of this on your right. The beauty of these oblique mounts is that they have adjustable points for 45 or 55 degree oblique mounting so that you're not limited. An example of a helipod is included here as well with some oblique options. Right, so at this point, we're going to move on from installation configurations, and we're going to dive into mission planning. Airborne Mission Manager, or AMM. You might be wondering if you can plan a flight for both hardware in the same software. The answer is yes. Airborne Mission Manager is Optech's flight planning tool, which has its own Google Earth-like digital globe with ground elevations and imagery built in. And what we did is actually input the phase 1 camera statistics into a config file so that the users can have accurate previews of project requirements, challenges, flight times using both LiDAR and camera. The example on the right is using the IXM 100 and 150F with 50 and 70 millimeter lenses respectively. This is our project settings page. So you're planning a LiDAR mission and you select your cameras you wish to use for this mission. In this case, 100 and 150 megapixel RGBs. As you can see on this slide, we graphically display the LiDAR and imagery over realistic ground and display color violations for known limitations. The idea is to plan a LiDAR area or take an area of interest in the form of a KML or a shapefile and convert that to a LiDAR area. The software will automatically convert this, and then you can choose to add camera options in a single mouse click. And you can select your triggering options for the existing LiDAR flight lines. Now, in this slide, you'll see examples of a LiDAR-only terrain sample, a camera-only, and then on the right, LiDAR and camera over realistic DEM and imagery. So we also allow the users of AMM to select specific camera features. If you're more interested in planning for a camera mission, you can also select automatic altitude selection for your required GSD on your project. And here's a few more features for the camera setup once the LiDAR area has been drawn. You can add camera trigger points to a LiDAR polygon or corridor based on time, overlap, distance, or fixed coordinates. So there's a number of different methods that you can see on the image on the right to add camera points. You can view immediate statistics on the predicted GSD, trigger interval time, footprint dimensions, total frame numbers, and expected project time. And if there's any scenario where you've asked the camera to trigger too quickly beyond its minimum cycle time, or you have terrain which changes beyond your GSD tolerance, the software will actually pick up on this automatically and flag it to the flight planner. So you can select your camera placement based on forward overlap percentages, which is the typical requirement or the typical method. And that way your overlap is consistent. And you can also select it for a wide area scenario, a side lap requirement for the camera. So you can plan your side lap with automatic flight lines filling a wide area, filling a polygon based on LiDAR or camera side lap values, because the field of view on these two is often different, although it's not far off. So you can also add a flight line buffer for altitude, which is a GSD-based selection. Or you can add additional frames at the beginning and end if you have a pitch angle or you're nervous about missing your AOI boundary for your imagery. Lastly, in the settings window, you can enter oblique angles that you plan to mount your camera. And the software will actually accurately display your oblique frames, as well as update you with views on frame dimensions, minimum, mean, and maximum GSD within a single frame. So a flight planner gets full insight into what they're going to expect versus their specific mounting configuration. Now, within the settings window in AMM, there's 3 tabs for planning your desired configuration, as you see in the picture below. Besides the LiDAR and camera tab, which I just covered, the third is for setting up flight lines using various modes. So we talked about a flight line buffer to automatically select your altitude for your GSD, and a colorized drawing of GSD frames where you may exceed your expectations. But you also get automatic flight line heading selection for maximum productivity in the air. You can select a specific number if you have any airspace restrictions, or have the software come up with the most efficient line heading. You can also plan based on minimum, mean, and maximum terrain per segment, or for the corridor in the line, or for the polygon for the mountainous terrain. This means that you're planning your altitude over the peaks, the valleys, or the averages, so that you can either guarantee your coverage, guarantee your GSD and densities, or average the both. AMM also has an automatic adjustment to line spacing for gap-free coverage based on realistic terrain heights. In one click of a button, the software will eliminate any gaps in your LiDAR and camera coverage. Now, Airborne Mission Manager also has some features that allow you to QA the data. There really should not be any surprises after you've flight planned effectively. There's also some outputs that are available. So you can graphically display violations for min capture rate and GSD tolerance based on your own input. The default is 10% variance from a GSD. But if you have hard limitations, which most do, you actually can output a statistics report. You can view the statistics report or output it as a CSV as well. And see this in the layer view, which is similar to other GIS software where you can view layers and apply different changes to different layers. So finally, you can also output a project report in the form of a PDF, which includes key technical specifications and time and cost information. It's a really good one-click output PDF for your project managers for your airborne missions. Here's an example. So once you've refined your mission plan, this is one of the CSV outputs from AMM. Although there are more columns that I cannot fit in this slide, the user can view minimum, mean, and max point density for LiDAR and GSD for camera, in addition to flight line statistics for every single planned flight line. This is great for airborne operators, where they can advise altitudes for pilots, as well as providing feedback on line spacing, distance to ground, flying altitudes above ground and sea level. These are also included in this this flight line output. So the main point on the planning is that we are using accurate imagery and terrains, and we do colorize any flight lines or any camera frames that don't meet your requirements, and the level of automation is also quite high. So I'm moving on now to what I would call the big show, the simultaneous collection of airborne LiDAR and imagery. Inner operators collect this data using a laptop and 2 pieces of software. Optech's FMS Nav for the LiDAR monitoring and triggering of the cameras, and Phase 1's IX Capture for exposure, white balance, thumbnails, histograms, and more. So we are using these 2 in conjunction. This image on the screen just shows a flight, an aircraft flying a corridor flight line. The trigger points are automatic, as is the LiDAR, and this is based on position and whatever triggering mode you flight planned. So when the aircraft hits the flight line, the LiDAR automatically gets triggered, and the camera automatically gets triggered at certain points. So FMS Nav will allow you to view image thumbnails. IX Capture will allow you to use image thumbnails. FMS Nav includes a camera diagnostic to confirm connection with the triggering module. It also displays camera trigger points and frames, which are accurate because it's pulling real-time information on the camera's field of view and the current roll pitch and heading from the IMU. So it is displaying your accurate coverage of your camera. Although IX Capture is preferred for making setting changes in air, FMS Nav will automatically trigger the camera, as we mentioned. In addition to displaying LiDAR and camera coverage, FMS Nav also includes the following for camera display. We include a counter of successful and dropped images included in the FMS Nav interface. We include frames which are colored based on position and orientation variation from a planned trigger point and horizon. And for my American friends, no, I did not misspell color. It does have a U where I'm from, so I'm going to say that now. We also include distance-based user input thresholds available for automatic trigger points. The frame borders will be colored appropriately when nearing or exceeding automatic triggering positions. So that means that if your roll pitch or heading cause your camera to be outside of its planned distance, it will flag the image. It will also flag the frame coverage if the image has been dropped for whatever reason, be it hard drive or minimum trigger times. Okay, so gyro-stabilized LiDAR. We can do 3 or 4 band imagery with the Galaxy in Optech's LF410 mount with a SOMAG GSM 3000 or 4000. You'll see this on the bottom left. That gray circle there is actually a shot up the bottom of an LF410 mount. That is the output window of a Galaxy and the lens on an IXU 1000. So the open port there will also allow NIR for 4-band. FMS Nav also has integrated drift correction through Applanix's position and orientation system. So in addition to seeing camera information, LiDAR information, you're also seeing the GSM encoding information. And I included some images there on the bottom of what some of your frames might look like if you have roll, pitch, and heading variation, which are completely eliminated by the GSM. This is sort of the ultimate setup for LiDAR and camera collection, in that both the LiDAR and the camera are being compensated for in one mount platform. And to provide additional insight to the operators, we also include roll, pitch, and heading thresholds of the GSM, which are also built into FMS Nav. So if you are exceeding the GSM's limitations, again, the operator has immediate insight into this, and you will not leave the area knowing that we haven't collected a certain portion of the AOI. As a final note on FMS Nav, these accurate camera frames I mentioned previously are automatically output as KML files, and these can be imported into Google Earth with attributes on planned speed, planned GSD, triggering methods, line start and stop time. This is all built into the camera frames, as well as the LiDAR coverage. Both of these are output from FMS Nav, and both can be immediately viewed in Google Earth as a QC tool. These can also be imported back into FMS Nav if you're doing a multi-day project. So even if you have a change of field crews, everyone should be able to see what was flown yesterday or what was flown on the same day. You don't have to rely on reporting to know what line to start on. All right, we're moving towards our last subsection. I'll go over the newly updated LMS Pro versions, which have incorporated camera bore sight processing into its already bore sight least squares LiDAR block adjustment as a multi-sensory bundle. So as you can see, through every step of the workflow, from the installation to the flight planning, to the mission data collection, and now into the data calibration and processing, we do have fully integrated phase one capabilities. So LMS is the software where we're taking raw imagery, raw LiDAR data, trajectory information, and instrument parameters, combining that all into a calibration model and outputs. It's a single software, multi-sensor data processing. So the advantage is that you can use the same control, the same tie planes to adjust the LiDAR as you can the camera. And then you can use these two data outputs to refine each other as well. So we're ensuring accurate LMS.
Mark, I think we lost you there for a minute. I don't know if you have some bandwidth issues, but I'll wait to see if you can get reconnected.
You lost me there for a minute?
Yeah, I did.
Everyone
Yep.
hear me?
Yep, now you're back.
Okay, so where did I leave off for you guys?
The LiDAR imagery and trajectory processing.
Right. Okay. All right. So I'll recap that quickly in case anyone missed that. A bit on LMS Pro on the fact that we can take the raw imagery from the phase one cameras, the LiDAR data from the Galaxy, instrument parameters for both from Planet and produce accurate, refined, and bore-sighted LiDAR and imagery. And not only do they use the same tie planes control points, but they can actually refine each other. So that's what I mean by accurate multi-sensor data co-registration. LMS also offers quality assurance processes and tools for both LiDAR and photogrammetric systems. So the photo block adjustment is now incorporated into LMS. We're doing our renowned bundle block adjustment with incorporation of GNSS and INS observations. Put an EL camera as well as files for the LiDAR. LMS has an automated tie point determination, so it can detect tie points based on features in multiple images. These can also be manually entered as well. And then you're using your control point incorporation for adjustments. It's really just, for the most part, a text file imported into LMS to make your corrections using a text file. Reporting tools through LMS. So our tools allow for observations, residuals, vision, checkpoint analysis, as well as distribution of tie points within the imagery. This image on the bottom left shows an example of a calibration plan that was flown with LiDAR and camera. There's 6 lines there, and then you're identifying cross lines for bore sight corrections. The image on the right is the automated type. So you can use that in conjunction with tie point selections for the imagery. Now you can do a quick assessment of the LiDAR and imagery alignment. The image on the bottom left is showing your LiDAR points over a roof line. This is ideal for the block adjustment and the calibration of the LiDAR because we use overlapping regions in the LiDAR to correct for minor scanner error. At the same time, you can also control that with imagery. So the imagery and the LiDAR are both over the same point, which you can do analyses on. On the right-hand side, we have a view of our events, which comes out of our trajectory file, as well as our EO for that line. As any of you who are in aviation know, it's very, very difficult to keep an aircraft steady when you're, several kilometers above the ground. A fraction of a degree of roll, pitch, or heading results in distortion of the image frame. So an EO is necessary for airborne collection. We can output this, and those are compatible with major photogrammetric software as well. So Optech's main goal is to calibrate, refine, and bore sight the imagery, get it as accurate as possible, and then allow our users to take that accurate georeferenced imagery and use their deliverables in a third-party software. So here's our output options from LMS. We can output a colorized point cloud. Now the LiDAR points, LMS allows the LiDAR points to automatically look for the nearest RGB value from a phase 1 camera, and that it assigns a realistic color to that actual LiDAR point. So although this may look like somewhat of an image, it's actually a LiDAR point cloud where the points are colored by the phase 1 imagery. So this co-registration allows for high quality colorized point cloud. This is just a few more examples of colorized point clouds. Sure, it's a pretty picture, but it's also useful. You can use these colorized points as an additional feature in classification. So colorized point clouds was was a requirement when we were adding this to LMS. But it's not only colorized point clouds. You can also output your georeferenced images in the forms of TIFFs, for example. Just one example. For various applications, there's many. One of the most common ones where you would use LiDAR to measure, for example, a sag analysis or pole identification for utility management. But you can also use the imagery to look for tower health, cracked conductors, things like that. And then, if we come back to my initial opening statement on opening up new applications purely by the combination of LiDAR and imagery, I think one of the nice examples is the fact that LiDAR is ideal for vegetation management for utilities. You can analyze a 3D point cloud to automatically identify vegetation that's within a certain threshold of the wires or conductors. However, four-band imagery, for example, takes it a step further. You can actually apply an NDVI index to that and not only assess which trees are at risk of encroaching with conductors, but which types of vegetation are dying or more likely to fall on conductors. And that's a very pricey bill for utilities companies as climate change increases and we notice more and more storms. We're seeing greater outages from vegetation falling on conductors, for example. On the right, you'll see a very old version of PLS CAD, which is used for a lot of the utility work. So that covers what I'd like to share in this session. I'd like to sincerely thank Phase 1 as well as our users for making this possible. If you have any interest in learning a little bit more about Teledyne Optech's LiDAR products with your existing imagery, please don't hesitate to contact myself or Teledyne Optech through my email or website. I do believe we're going to open up a little bit of Q&A to close out the webinar. So I'd like to thank you all again and wish you a great day.
Thank you so much, Mark. What a very informative outline of all the integration that was done with the Phase 1 and your Teledyne Optech sensor, just from the beginning of flight planning all the way through to the output. Very impressive, and thank you so much for sharing that with this group today. So I'd like to open it up to our question facilitator, Paula Cooper, to see what kind of questions we have and what we can answer there.
Hi there. Yeah, there's a couple of questions come in. One was, how many camera modules can each mounting configuration support?
Oh, right. Okay, so we discussed the fixed mount with the Galaxy and the Phase 1. This will support either 1, 2, 3, or 4 camera modules. And these can be RGB, dual RGB, 4-band, and any combination of the above. So that's the fixed mount. There's also the gyro-stabilized mount in the LF410. That will hold 1 or 2 camera modules. So we can do RGB, dual RGB, or 4-band. And then finally, the carbon fiber mount, which is mountable in a helipod or fixed wing, can support up to 5 camera modules. And then the IX controller can support 6, although Optech's mounts, we provide 5 max on the obliques. Good question.
Thank you. I've also got, how do you ensure consistent forward and lateral overlap of the images? And also, what are the suggested overlaps?
Okay. Typical project overlap would be, I would say the most common is 60% forward overlap. Most are looking for a minimum 50 for orthomosaics. You want to have lots of overlap so that you can tie images together for your mosaics. And the lateral is more based on LiDAR. With our setup, most commonly You set up a LiDAR side lamp. I would say the industry average, although it greatly varies, is approximately 30%. But the advances of swath tracking and terrain tracking can reduce this overlap percentage, which really increases your efficiency if you have access to swath tracking. Now, there was a part of that question which I haven't covered. Now, that's the percentage. How do you maintain that? Typically, older generations of cameras would trigger by time, and if you have a headwind or tailwind when you're flying your flight line, you actually gain or lose some of that percentage. So if you're planning based on a fixed GPS position, based on a percentage, which is my advisable way of doing this, even if you have headwinds or tailwinds, you're going to maintain your consistent overlap.
Okay, thank you. There's another question. Can you support ortho, mosaic, and 3D imagery?
Through LMS, we do not. Optech focuses on the calibration and refinement. That is the main goal of LMS, is to get this as accurate and calibrated as possible. Many of the users also have their preferred software for doing orthomosaics and 3D wrapping. But no, LMS will output calibration files, the EO, and colorized point clouds for use in third-party software.
That leads on to the next question, which actually says, what are the advantages of outputting a colorized point cloud other than just a good-looking picture?
Right. It does look cool. We talked a little bit earlier about classification. Typically classification is using range-based, some feature extraction, but largely it's the LiDAR intensity, and that's LiDAR alone. So you are limited to classifying some objects with LiDAR alone. The imagery can add a whole new set of variables to increase your confidence in classification. So if you have an RGB value assigned to a point, this really assists with point cloud classification. Some of the buzzwords I'm hearing around LiDAR and camera right now is automated data mesh, automated feature extraction, and so that seems to be the way a lot of LiDAR and camera users want to go. And now they want full data mesh. The problem is the LiDAR resolution hasn't quite caught up to the imagery. The imagery is really high resolution, and we need to match that with the LiDAR to increase our capability of automated feature extraction and a full data mesh. And so I think that's where this is going, and I think that's where LiDAR and imagery do have a future together.
Okay, thank you. I think we've probably got one more question. Was, how does AMM ensure accurate display of predicted camera frames and any GSD expectations?
Okay, another good question. So we have the known phase 1 camera sensor statistics built into AMM. So we know what the phase 1 can do. We're also using realistic and accurate DEMs for a global source, as well as imagery in AMM. So if you know exactly what the camera can do, and you know to a certain extent what the ground is in all the area that you're planning, it's actually quite easy to know what your GSD is going to be for every frame, and output your min, mean, and max GSD, as well as your frame sizes and expectations on the project requirements.
Okay, thank you. That's it. There was just one more question. So I did just check that the recording will be available online. Yes, it will. All of our webinars will be available online on our website. So that's it. I'll hand you back to Dana, and thank you very much, Mark.
Thank you, Paula. Thank you, Mark, for answering those questions. This has been a very informative webinar. I do appreciate, Mark, you participating in this from Teledyne Optech. I also want to give a heads up to those that are on the line that we have some interesting ones coming up in the next couple of months. So I urge you to pay attention to those upcoming webinars to take a look at those, diving deep into some specific market segments and some users of our products on the end user perspective. So thank you again for joining our webinar, and have yourself a wonderful and great day.